Hello, my name is Adnan Yunus. I work as an ML engineer in Latent AI. My work revolves around deploying AI models on the edge and creating tests that effectively benchmark our software infrastructure. Part of my work is involved in and exploring new domains of research that our platform has not have exposure to. A primary example of this is radio signal classification, specifically analyzing a waveform, seeing its modulation, and determining the type of waveform that it is based on that sort of information. Such information can be useful for intercepting certain hostile communication signals, or can be used to create a filter of permissible signals that are allowed to pass through a network. Some of our customers who develop radio frequency models really want to host them on the edge. This is particularly challenging, however, because experts who work in remote areas have no Wi Fi access and it is difficult to communicate information between two devices. Also, radio frequency models have high memory requirements, ranging from the megabytes to terabytes of information. This makes storing inference at the edge difficult, but thankfully, LEAP Optimize is here to save the day. LEAP Optimize takes models and streamlines their operation by adjusting internal representations and instructions. Importantly, the speed is increased and the energy or the load on the CPU is drastically reduced, and the accuracy is maintained. It works like magic and is able to take any large neural network and take it to new heights. Let me show you a demo.
Here is a demo of LEAP Optimize in action. So on the left code window, I'm training a radio frequency model. This is the data set I'm using and the tags. Then I'm just using boilerplate PyTorch to create a model. Just through inspection, we know that this is a very, very large model, and it'll be difficult to store this on the edge. I trained till completion, and then at the end, I evaluate the model. So you can see that our accuracy ranges from 87.58% to 98.71%. What we did is we took that model and then used Forge to optimize it for the Jetson AGX environment. And that's what this right code block is trying to show. Now we took the same code and we put it through, and we can see that the accuracy is pretty much the same within 2 to 4 significant figures. One of the cool things is that on the right, you can see we actually worked with the full batch of the training set, versus here, we had to do 133 batches of 128 length training sets. And then we also get less number of iterations per second. So we know, just looking at this output block, that our compute time and other sources are used much, much less. 30.68 iterations per second versus here we're using 98.82 iterations per second. This is a table we have when we present it to the client. It's the same model. Bottom is the optimized model on the AGX. We see that the GPU memory is drastically reduced by 3 factors over, and the inference rate is reduced by 12 factors over, and the energy on the CPU is reduced by 10x, and the accuracy is preserved in this case.